the ambition to harness the full radiative output of a star, a concept famously formalized by physicist Freeman Dyson in 1968, remains perhaps the most profound engineering challenge conceivable within the bounds of current physical understanding, an aspiration that transcends mere technological advancement to touch upon the very existential trajectory of a civilization, moving it decisively from a planetary-bound entity to a true stellar species, a Kardashev Type II civilization, on the widely accepted scale of technological maturity. To even begin to contemplate the construction of a Dyson sphere, or more realistically, the more tractable Dyson swarm or Dyson bubble configurations, one must first grapple with the staggering scale of energy involved, a scale that dwarfs any terrestrial energy generation scheme imaginable today. Consider Sol, our own Sun, an average G2V main sequence star, which radiates energy at an astonishing rate, roughly 3.86 times 10 to the power of 26 watts, a value often denoted as 3.86 from the 26 watts, representing the total solar luminosity, a figure so immense that even capturing a minuscule fraction of it, say 1 part in a trillion, would provide an energy budget many orders of magnitude greater than the current total energy consumption of all human activity on Earth, which hovers around 15 terawatts, or 15 times 10 to the power of 12 watts. A gulf that illuminates the necessity of such mega-engineering projects. For any long-term interstellar expansion or sustained high-energy computation, such as the theoretical requirements for simulating entire universes or maintaining vast artificial intelligences. The theoretical underpinnings of a full Dyson shell, a solid, static enclosure completely surrounding the star, present immediate, insurmountable problems rooted in fundamental physics and materials science, a static shell, to maintain its structural integrity against the immense gravitational pull of the star, would require materials possessing tensile strengths far exceeding anything presently known or even theoretically predicted for stable, bulk matter under standard temperature and pressure regimes. Indeed, the required compressive strength to prevent gravitational collapse would necessitate materials with densities comparable to neutron stars or perhaps even quark matter, materials utterly beyond the reach of conventional chemistry or metallurgy, essentially demanding the manipulation of fundamental nuclear forces in a macroscopic structure, a prospect decidedly in the realm of science fiction rather than near-future engineering. Furthermore, the orbital mechanics present an immediate paradox. A solid shell cannot orbit its central star in a stable Keplerian manner. If the entire structure were to move as one rigid body, it would inevitably spiral inward due to tiny perturbations or asymmetries, or if designed to be perfectly stationary relative to the star's center of mass, it would require continuous, active station-keeping propulsion systems of unimaginable power output just to counteract tidal forces and slight gravitational imbalances, essentially making the shell a giant, complex spacecraft rather than a passive energy collector. This inherent instability has steered serious theoretical discussion toward the more plausible, albeit still monumentally difficult, concepts, the Dyson swarm and the Dyson bubble. The Dyson swarm, often considered the most viable pathway, consists of a vast collection of independent, individually orbiting collectors, satellites, or habitats, perhaps thousands of kilometers in diameter, positioned across a spherical volume enveloping the star, potentially stretching out to several astronomical units. With one astronomical unit being approximately 149.6 million kilometers, the average distance between the Earth and the Sun, these collectors would be dynamically independent, each following its own prescribed orbit, much like the planets in a solar system, thus bypassing the structural integrity and orbital stability issues of a solid shell, relying instead on established celestial mechanics for their placement and motion. The advantage here is scalability and redundancy. Construction can proceed incrementally, starting with a small cluster of collectors and gradually increasing the coverage as material and manufacturing capabilities allow, perhaps commencing with collectors placed at the distance of Mercury, or even closer to the Sun to maximize flux capture efficiency, though the thermal management challenges would escalate dramatically. The second theoretical construct, the Dyson bubble, proposes using a constellation of structures held in place not by their own orbital momentum but by active propulsion or perhaps by the steady outward radiation pressure from the star itself, if the collectors are designed with extremely large, lightweight sails or reflective surfaces. This configuration is structurally less rigid than a swarm but potentially allows for greater control over the placement and orientation of the collectors, although it introduces the engineering overhead of maintaining propulsion or attitude control for every single component in the constellation. However, even the Dyson swarm presents material science hurdles that stretch current capabilities to their absolute breaking points. The sheer surface area required to intercept a significant fraction of stellar output is breathtaking. If humanity decided to enclose Earth's orbit, roughly 1 astronomical unit from the Sun, the surface area of the required sphere would be about 3.01 times 10 to the power of 19 square meters. A region so vast that covering even 1% of it with photovoltaic arrays would require the complete dismantling and reprocessing of virtually all known terrestrial resources, including perhaps every asteroid and moon within the inner solar system. The sourcing of this monumental quantity of material is the first practical roadblock. Estimates suggest that the mass required for a full shell at 1 astronomical unit, using materials with densities comparable to terrestrial aluminum or silicon, would be several orders of magnitude greater than the mass of the Earth itself, approximately 5.97 times 10 to the power of 24 kilograms. Therefore, the construction of any large-scale Dyson configuration necessitates a thorough and complete transition to an off-world industrial base, a space-based economy capable of asteroid mining, Kuiper belt object resource extraction, and perhaps even dismantling entire terrestrial planets or large gas giants for their constituent elements, a process termed planetary engineering or stellar resource utilization, a term popularized in futurist literature. Current space resource utilization is embryonic, focused primarily on extracting water ice for propellant and life support, but scaling this up to construct megastructures requires mastery of autonomous robotic manufacturing, in situ resource utilization, or ISRU, on a scale never before imagined, utilizing technologies like solar concentrators for smelting and additive manufacturing that operates in zero gravity and hard vacuum. Material science itself must evolve dramatically. The collectors need materials that are exceptionally light, highly reflective or absorptive across the star's emission spectrum, capable of withstanding extreme thermal loads, and possessing superior radiation hardness over timescales measured in millennia, since the structure must endure the star's life cycle. Terrestrial silicon-based photovoltaics, even the most advanced multi-junction cells achieving efficiencies nearing 35% under optimal laboratory conditions, are likely too bulky and thermally sensitive for deployment near the star. Future collectors might utilize metamaterials engineered at the nanoscale to perfectly tune absorption and emission properties, perhaps involving synthetic diamond lattices or carbon nanotubes structured into vast, thin films capable of radiating waste heat efficiently into the coldness of space at infrared wavelengths while capturing visible and ultraviolet light. The thermal gradient is critical. Any collector operating too close to the star, say at an orbital radius equivalent to Mercury, about 0.39 astronomical units, would experience thermal loads demanding operating temperatures well over 500 degrees Celsius, far exceeding the capabilities of most conventional electronics and structural alloys. Beyond the material challenges lies the energy transmission problem. How does a civilization utilize the captured energy? If the collectors are in a swarm at a distance equivalent to Earth's orbit, the energy must be beamed back to population centers, whether those centers remain on Earth, reside on modified planetary bodies, or are themselves space habitats. Line-of-sight power transmission, utilizing highly collimated microwave beams or phased array lasers, becomes the only practical method for distributing petawatts or exawatts of power across vast interstellar distances, maintaining the necessary beam coherence across millions of kilometers against atmospheric distortion or interplanetary dust interference requires extremely large transmitting and receiving apertures, demanding precision pointing accuracy measured in nanoradians. Furthermore, the efficiency of this transmission must be near perfect, as any waste heat generated during the conversion process adds to the thermal burden of the swarm itself, potentially leading to thermal runaway, and less sophisticated heat management systems are integrated into every collector unit. The motivation for embarking on such a monumental endeavor stems from the finite nature of planetary resources and the long-term thermodynamic imperative of intelligent life. Earth currently relies on a combination of fossil fuels, nuclear fission, and increasingly, renewable sources like solar and wind. But even if humanity achieved a 100% renewable global energy system utilizing all available insolation on Earth's surface, which is limited by the planetary cross-section intercepting sunlight, that total energy budget is still orders of magnitude too small to support the energy demands predicted for a true spacefaring civilization, especially one engaged in large-scale computation or interstellar travel, which involves propulsion systems requiring colossal energy densities. the transition to a Dyson swarm represents a civilization's first assured step beyond the constraints of its birth star's meager planetary surface, securing power availability for millions, perhaps billions, of years, given the Sun's projected main sequence lifetime of approximately 10 billion years. The detection of potential Dyson structures, or technosignatures, remains a key area of astrobiological research, often categorized under the SETI framework, though focused specifically on astroengineering rather than communication signals. Astronomers search for objects that exhibit anomalous infrared signatures inconsistent with known astrophysical phenomena. A partial Dyson swarm, for instance, would absorb the star's visible light and re-radiate the energy at the star's black body temperature in the infrared spectrum, slightly cooler than the star itself, resulting in a light curve that shows periodic dips in visible light corresponding to the passage of the massive collectors across the star's face, coupled with a persistent, large excess of mid to far infrared radiation. The most famous historical candidate was Tabby's star, KIC 846250, which displayed highly irregular, deep, and non-periodic dimming events, perplexing astronomers until later analysis, incorporating data from the Spitzer Space Telescope, suggested that large, irregular clouds of dust or perhaps large planetary fragments in highly eccentric orbits were the most likely explanation, rather than a structured megastructure, although the initial excitement underscored the profound impact such a detection would have. More recent efforts focus on analyzing large photometric surveys like those conducted by the Kepler and TESS missions, searching for the specific spectral signature of a nearly enveloped star, a clear shift from stellar radiation to thermal emission consistent with large, opaque artificial structures. The timeline for such a construction remains speculative, deeply contingent on breakthroughs in fundamental physics and economics. If a civilization achieves true post-scarcity, perhaps through mastering fusion power or zero-point energy extraction, the sheer economic incentive to build a Dyson swarm might accelerate construction dramatically. However, using even current projected growth rates, assuming an exponential increase in space industrial capacity, perhaps doubling every 50 years, the construction of a substantial swarm covering, say, 10% of Earth's orbital area, might still take several centuries to a millennium, provided the initial industrial base is established far beyond Earth, likely starting with the Moon and Mars, and rapidly expanding into the asteroid belt where material is readily available without the energy cost of deep gravity well escape. Early stages might involve deploying vast solar sails near Mercury to power initial automated manufacturing hubs, which would then begin processing near-Sun asteroids for raw materials, employing orbital mechanics, specifically utilizing Oberth maneuvers and gravitational assists, to move refined components into the construction zone. One crucial aspect often overlooked in simplified discussions is the waste-heat paradox of advanced civilizations, articulated by economist Robin Hanson. Any advanced technological process, especially one involving the capture and conversion of enormous amounts of energy, must necessarily dissipate waste heat into the environment, dictated by the second law of thermodynamics. A civilization utilizing the full output of its star, a Kardashev Type II civilization, will inevitably radiate energy corresponding to the star's total output, albeit at a lower temperature, likely in the far infrared region, around 300 to 1000 Kelvin depending on the efficiency and spacing of the swarm elements. Therefore, the search for Dyson spheres is fundamentally a search for an abnormally high level of infrared emission originating from a compact region of the sky that lacks a correspondingly large visible light source, or where the visible light source is significantly obscured. This infrared signature is a universal and unavoidable technosignature, regardless of the civilization's current technological focus or communication preferences. Furthermore, the construction process itself might leave behind distinct markers. The immense energy required for mining and refining materials, even in space, will produce transient thermal plumes and unique spectral emissions from large processing facilities, which might be detectable long before the final, optimized swarm structure is complete. Simulations suggest that the early, messy stages of construction, the construction phase debris field, might look very different from the perfectly ordered final product, perhaps presenting as a diffuse, non-Keplerian cloud of warm, non-gravitationally bound objects, which could confuse initial attempts at classification. The philosophical implications of achieving Dyson-level energy control are staggering. Such a civilization would have effectively guaranteed its physical survival for the remaining lifespan of its star, rendering it immune to terrestrial catastrophes, resource depletion, or even the long-term evolutionary pressures that limit life confined to a single planet. This energy surplus would enable endeavors currently confined to pure speculation, interstellar travel, perhaps through massive laser-pushed light sails accelerating probes to relativistic speeds, manipulation of stellar output, allowing the civilization to fine-tune the star's habitable zone by slightly altering the size or spectral output of the swarm, effectively managing the stellar life cycle, and the creation of vast, artificial biospheres or computational substrates contained within the sphere itself, perhaps utilizing the entire inner volume for computation or habitat, a process known as matryoshka brains if the structure is designed specifically for computational density, where successive layers of collectors harvest waste heat from the previous, hotter layer, pushing thermodynamic efficiency to its theoretical limits. In summary, building a Dyson swarm transitions humanity from a precarious planetary existence, vulnerable to asteroidal impact, supervolcanic eruptions, or self-inflicted ecological collapse, to a state of near immortality constrained only by the laws of physics and the eventual fate of the star itself. It demands revolutionary breakthroughs in robotics, autonomous manufacturing, extreme material science capable of operating under intense radiation and thermal stress, and a complete overhaul of our economic paradigm to support off-world, high-volume industrialization. While the solid shell remains a dream hampered by gravitational and material limits, the swarm represents a concrete, if staggeringly difficult, engineering trajectory, the logical next step for any civilization seeking to maximize its cosmic potential by claiming the entirety of its local stellar power source. The journey begins not with megaconstruction, but with the first successful autonomous mining operation on an asteroid, the first self-replicating robotic factory placed in orbit, and the first truly robust long-duration power transmission demonstration between the Earth and the Moon, incremental steps paving the way toward transcending the light and shadows of a single, small blue marble.